All right, so we're just about ready to finish off Unit 3 with this last topic of Lesson 3. And what we're going to be discussing is something called linear programming, or in some cases we call it linear optimization. And what this really means is that we're going to take systems of linear inequalities and find out what kind of useful information they can give us in the real world. In order to kind of help you connect to the example that we're going to talk about here, I'm going to start out with a real life example. So instead of starting out with the math and then doing the real life example after, we're going to start with the real life example and work towards the math part. I'm going to take notes down on my screen as I talk, and I want you to copy them into your notes as well. So take a look at the screen and listen to my little story as we go. So let's suppose that we have a person who is a salesman, and this salesman has two objects. We'll call one X and one Y. I'm going to assume it's something maybe like technology, something that that takes up a good amount of space but could be really valuable, can be very profitable to sell technology, but it's not easy to transport. So let's suppose that this person is going on a little exhibition tour, like a business trip, and they are allowed to bring at most 5 objects. So we have X and we have Y. So X, one could be like an iPad and one could be a Chromebook or something like that. So they're allowed to bring at most 6 objects. And they are also need to keep that number under 10 pounds for the objects, because they only have 10 extra pounds left in their suitcase. And we will say that item X weighs 2 pounds and item Y weighs 1 pound. So I'm not taking down any notes yet, but you can just keep those ideas in the back of your mind. So first thing that I said is that the first limitation for this salesman is that he or she can only bring 6 items. So how might I explain that? I am going to add up. Let's say X counts for the number of, let's say we'll call this a Chromebook. And we'll call this an iPad. And we're going to say that the number of Chromebooks plus the number of iPads must be less than or equal to 6. It's just, let's say that that's a limitation that's being enforced by whatever the sales group is. And we also know, we're going to say that the Chromebook weighs 2 pounds, and so that's 2 times the number of Chromebooks would give us the number of pounds per Chromebook. And we're going to say that the iPad weighs 1 pound, so that would be plus 1Y, or just Y. So 2 pounds per Chromebook plus 1 pound per iPad, and we said that this person only has 10 pounds left in their suitcase. So that number has to be less than or equal to 10 pounds. And then we're also going to say that obviously we're dealing with real stuff, so we can't have negative numbers. So X needs to be greater than or equal to 0. And Y also, the number of iPads needs to be greater than or equal to 0. And this is our system of inequalities. And we got all of that information from real parameters. The first one again was the salesperson was only allowed to bring at most 6 items, and the second is that we can't exceed 10 pounds, and then of course we have a limitation based on the fact that we are dealing with real items. We can't have negative Chromebooks or negative iPads. Okay, that being said, let's suppose that this salesperson is able to make a profit of $400 per Chromebook and $100 per iPad. And the reason I'm saying that, you're probably thinking, yeah, but why? The iPads are often so expensive. But Apple's my husband sells technology. Apple doesn't like to doesn't like to give a lot of profit to other people. So let's say that we get, we're going to make this 4 be a $400 per Chromebook in commission, and let's say $100 per iPad, so that would be 1Y, and that would be the profit that this person is going to make. And the idea here is we have quite a few parameters, and we don't know. This person can only bring up to 6 items. They can only bring up to 10 pounds, and but they want to maximize their profit. They want to make sure that the number of objects that they're bringing are going to maximize the potential money that they could make. So we don't want to get a whole bunch of iPads because we can't make as much money on them, but we don't want to bring a whole bunch of Chromebooks because they weigh a lot, and so we can't bring as many. So that being said, let's see how linear inequalities, or graphing systems of linear inequalities, is going to help us find the answer to this real life problem. The first step, of course, is that we need to graph them, just like we did in the last section. So let's use a couple different colors here. I'll start with pink. And let's look at this first equation. Now you'll notice x plus y is less than or equal to 6 is not a graphable equation. We need to put it into y equals mx plus b form. So the way I'm going to do that is I'm going to subtract x from both sides of this equation. And when I do that, I will get, I'm going to write it over here, y is less than or equal to negative x plus 6. So that's just me rewriting that first equation into y equals mx plus b form. Now that means that we have a y-intercept of 6, which is 1, 2, 3, 4, 5, 6 right here. And a slope of negative 1. So that's down 1 over 1. Down 1 over 1, down 1 over 1, and so on and so forth. And that will be a solid line because it is less than or equal to. Speaking of less than or equal to, that means that we need to shade in this area underneath. Now, instead of, well, actually, yeah, I guess I will. If you don't want to shade right away, you could actually write like little arrows to yourself, and then like as a note to self, and then shade the common area at the end. But I think I have enough colors here. I can make it work to shade it off. All right, that is equation number 1. Let's look at equation number 2. We'll do it in green. This is the limitation enforced by the weight. So we have 2x plus y is less than or equal to 10. Again, this is not a graphable equation yet, but if I move the 2x over to the other side, so subtract 2x from both sides, I will get y must be less than or equal to negative 2x plus 10. So this means I have a y-intercept of 10, so this was 6, right? So 6, 7, 8, 9, 10. And we have a slope of negative 2, so that's down 2 over 1. Down 2 over 1, down 2 over 1, down 2 over 1, and so on. So we're going to draw in that line. Again, this is a solid line because we can go up to 10 pounds, including the 10 pounds. And it is less than, so we're going to shade all the area underneath it. And then lastly, we have x must be greater than 0 and y must be greater than 0. So what that means is that we can't cross over these boundary lines. So here's x is greater than 0 from here on over, and y is greater than 0 from here on up. So anything that is in the in this first quadrant of the coordinate plane is going to work. So I don't need to actually shade for that. That just means that the axes are our boundaries here. Okay, so I've graphed our system of linear inequalities and I've found a common area. So let's use like orange here, and starting at this point down to the origin and then over to here up to the point, what is that, 1, 2, 3, 4, 2, and back up here. This is our common area. And this represents all the possible combinations that we could make of Chromebooks and iPads. So for instance, if I chose like this point right here, it would fall within the region. That's one iPad and one Chromebook. Or I could choose this point over here, which is what did we say? This is X. So this is 2 Chromebooks and 3 iPads. I know it's hard to see because I drew over our lines. And actually, that being said, I had an intersection of 6. So this should be what? Let's see, 1, 2, 3, 4. Oh yeah, 5. We're okay. I want to make sure that I hadn't skipped a spot. So let's see. Let me label these points. So this is 0, 0. Over here we have 5, 0. This is 4, 2. I'm just labeling the corners, and this is 0, 6. Now here's something interesting about linear programming. Whenever we graph a region that is within our constraints, and we're trying to figure out, in this case, we want to maximize the amount of profit that this person could make. We don't want to try every single possibility within this orange region. That would take forever. Well, actually, it wouldn't take forever because in this case, we only have to use whole numbers, right? Like, I can't have 1.5 Chromebooks and like 4.5 iPads. I can't do that. So I guess that we have a limited number, but it still would take a long time to plug in every single point within this orange region. We don't want to do that. And we don't have to, because as it turns out, whenever we're trying to optimize a region in linear programming, we only have to plug in the corners of the figure to find, or I should say, the best case scenario is always going to exist in one of those corners. And that's because those corners represent, in a sense, like maximum or minimums, or what we call extreme values in mathematics. They're going to give us the best and the worst possibilities without having to do all the other stuff. Is just like kind of somewhere in between. So if I want to know either the best or the worst options, they're going to exist in one of those corners. So that means I only have to figure out if 0, 6, so that would be 0x, 6y, so that would be 0 Chromebooks and 6 iPads. 0 Chromebooks and 0 iPads. I think we don't even have to try that. We know that would be our worst profit, right? 0 of each, that would be a bad profit. 5x, 0y, that would be 5 Chromebooks and 0 iPads. Or 4x, 2y, that would be 4 Chromebooks, 2 iPads. So which one is the correct, which one is the best use of space? And the way we do that is we plug it into our profit equation. Let's see what happens. So up here I'm going to say what would be the profit I'm going to just label it like this, profit for 0, 6. And the way we'll figure it out is we'll just say that would be 4 times 0 plus 6. So that would be, this is hundreds of dollars that we'd make. 4 times 0 is 0, plus 6 would be, we'd make $600. Or maybe I shouldn't say equals, I should put an arrow, because that'd be equals 6, which maybe I should, here, let me write it like this, because I'm going to confuse somebody, and I don't want to do that. So we'll say equals 6, and that represents $600. Okay. Let's try the next one. So let's see what the profit is for 5, 0. I'm not even, like I said, I'm not going to do 0, 0 because I already know that would make me $0. So that would be put into the profit equation, 4 times 5 plus 0. So that equals 20. So that's the equivalent of $2,000, $2,000, which would be 2,000. And then lastly, let's do 4, 2. So the profit for 4, 2. That would be 4 times 4 plus 2, which would be 16 plus 2, which is 18. So that would be the equivalent of $1,800. All right, so the question is, we know that the best case scenario is going to exist in one of these corner points. And looking at our choices, we find that our middle one, where's my arrow here? Our middle one, 5 Chromebooks and 0 iPads, is actually my best case scenario. Using it, it allows me to bring 5 objects, so that's less than or equal to 6. It allows me to use all 10 pounds that I have left in my suitcase, and it earns me the potential, if I sell all 5 items, I make $2,000. As opposed to if I brought 6 iPads, I would only use 6 pounds, but I'd only make $600. Or I could do the 4 Chromebooks and the 2 iPads. Again, that would maximize my 10 pounds. It actually would maximize my amount of items, 4 and 2, that would give me 6 items, but I actually don't make as much money because I can make more money with the Chromebooks. So there you go. That is your example of how to maximize profit using a system of linear equations. Now, I should say there are 2 types of linear programming problems. One is, and I'll just write this quickly, so one type is where we try to maximize, we find the maximum for a profit equation. That's what we just did. We have an equation and we want to find out how to make the most money. The other possibility is we could try to minimize a cost equation. And so you'll often see equations like P equals blah, 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 blah. That's what I just did. Or you'll say C equals da, 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 da. And if you think about it logically, whenever we have a profit, we always want to make it, we want to maximize it. We want to make it the largest it can be because that's how we make the most money. And whenever we have costs, and we could have the same situation where we have all these parameters, but how much does it cost us? We always want to minimize cost, right? That's good economics. Maximize profit, minimize cost. And we will talk about that in class. We'll look at a couple examples, but now at least you've seen an example for yourselves. All right, that should do it. You are done with lesson 3.